Chemistry, we're now moving on to another type of stoichiometry. We've been working with grams stoichiometry, that is grams to moles. Now we're going to be dealing with solutions. We'll define what a solution is. It's a little bit more sophisticated than what we've been doing, but after a little practice, you'll catch on. So a mixture consists of a combination of two or more substances. Mixtures can be homogeneous, meaning any part of the mixture is the same as another part. Think of a pitcher of Kool-Aid. The first glass you drink tastes the same as the last because the Kool-Aid powder is mixed homogeneously throughout the pitcher. A heterogeneous mixture is not uniform throughout. Think of a fruit salad. One spoonful might have a grape and a pear, while another spoonful might have a banana and a strawberry. There are three types of mixtures in chemistry. 1. Solutions produce molecular-sized particles of a solute that are dissolved in a solvent to produce a homogeneous solution. 2 are colloids. Colloids produce between 1 and 1,000 nanometers particles. Colloids usually stay suspended in the solvent. So milk, for example, there are fat globules, little tiny fat globules and protein globules in the water. So the water is the solvent and the protein and fat are these solutes. Third are suspensions. Suspensions contain particles larger than 1,000 nanometers. Often the particles of a solution settle on the bottom of the container, as you see in that picture right there. Since chemistry deals with interactions on the atomic and molecular level, we will speak only of homogeneous solutions in this class. A solution consists of a solute dissolved in a solvent. So the simple examples, think of lemonade. The lemonade powder is the solute. It's what's going to be dissolved. And that's 6 letters long. I'll tell you the significance of that in a second. You mix that in a solvent, in this case water. In fact, the solvent throughout this class is always, except with very, very rare exceptions, is always going to be water. And that's 7 letters long. The word solvent is 7 letters. And that equals the solution, and that's the mixture of the lemonade powder and the solvent. So you think of water. Water is a liquid in liquid form. As long as it's in liquid form, it is a liquid. But the moment you mix something in it, we no longer call it a liquid. We call it a solution. And the solution is a mixture of two things, a solute and a solvent. And the word solution is 8 letters long. So the way to remember it is when you mix lemonade powder and water to get lemonade, a lemonade drink, the solute, the thing that there's the least of, is the smallest word, 6 letters long. The next is solvent. That's 7 letters long. That's the thing that there's the next most of. And finally, when you put them together, that's the thing you have the most of. That's the solution. That's 8 letters long. So that's one way to remember the difference between solute, solvent, and solution. The primary measure of concentration is molarity, abbreviated capital M. Probably 98% of the measures of concentration we use in this class, 98% of the time we use a measure of concentration, it will be molarity. Molarity is moles of solute, think of the lemonade powder, over liters of solution. That's not the water. That's the lemonade powder and the water mixed together. If glucose is dissolved in water, we have the following. Solute is the glucose, solvent is the water, and the solution is the two of them mixed together. Usually we represent solution as SOLN. So when you see SOLN, it means the solute and the solvent added together. A 2 molar solution of glucose is written as 2 moles of glucose over 1 liter of solution, where SOLN represents the glucose plus the water. So study that, how that is set up there. That's called a derived unit. It's made up of 2 different units, moles and liters, and that creates a unit called molarity. Okay, so here's a beaker. So imagine that each group of 10 CO2 molecules in the beaker below represent 1 mole of CO2 homogeneously mixed in 1 liter of solution. So the solution is the water plus the CO2. So there's 10 symbolic molecules, particulates, particulate diagram, and that's 1 mole of CO2. And then down below you have another 10, that's another mole. So in that liter of solution, you have 2 moles of CO2. So a 2 molar solution has 2 moles of solute, CO2, in 1 liter of total solution. That's CO2 plus H2O, and that's a homogeneous mixture. The particulate diagram represents 2 moles of CO2 molecules in 1 liter of water. This is a molar concentration of 2 moles of CO2 per 1 liter of water, or 2 molar, 2 capital M. So let's assume that the solution is homogeneous. What would the molar concentration be if we poured half of the solution from the beaker? So right now it's 2 molar, 2 moles per liter. What would it be if we poured half of that solution out? So assume that the solution is homogeneous. What would be the concentration if we poured half of the solution from the beaker? Well, half the solution we poured out, so that's the blank area up above, and you also poured 1 mole of CO2. That's gone. There would still be then 1 mole of CO2 and half a liter of solution left. So to do the calculation on that, this is a concentration of 1 mole of CO2 over half a liter of solution, or 2 molar. So the concentration would not change. So think about the pitcher of Kool-Aid. The first cup tastes the same as the 5th cup. That's because the concentration in each cup of the Kool-Aid mix is uniform. It's the same throughout. Molarity. Now we're going to go over the measures of concentration, and by far the most important is molarity. It's moles of solute over liters of solution. Again, that's solute plus solvent mixed together. Next is molality. Occasionally we use this. That's moles of solute, so it's the same as molarity on the top, but it's over kilograms of solvent. So it's both a mass, not a volume, and it's not the solution, it's over the solute. So the bottom, the denominator is different. Mass percent is the grams of solute over the grams of solution times 100%. That'll tell you what percent of the solution is the solute. Mole fraction, somewhat similar to mass percent, except it's done in moles. So it's moles of one solute over moles of all solutes and the solvent together. You don't multiply this by 100%. Should point out that you can have more than one solute in a solution, but for our purposes initially we're just going to deal with one solute in the solvent. And then parts per million, that's done exactly the same way as mass percent. It's grams of solute over grams of solution, except you multiply by 1 million instead of by 100%. That's used when there's very small concentrations of the solute in the solution. Finally is dilution, and dilution is the molarity before the dilution times the volume. That's going to equal the molarity after the solution times the volume after the solution. This is the lemonade problem. You make your lemonade and it's too strong, it's too sweet, it's too syrupy. So what do you do to it? You pour more water into it to dilute it. That's what dilution is. It's adding water to make something thinner or weaker, or less concentrated is the proper way to say that. Density is defined by the amount of mass contained in a volume. In solution stoichiometry, it is usually means grams of solution per milliliters of solution. Often density is stated in a problem as follows. The density of salt water is 1.09 grams per milliliter. This is the abbreviated form that I told you you'll often find in problems. But you can turn that into an equivalency. This can be represented by the equivalency 1.09 grams of solution equals 1 milliliter of solution, where salt water is the solution. Salt is the solute, water is the solvent, and salt water together is the solution. The conversion factors for that equivalency would be, hopefully by now this is automatic for you to be able to get conversion factors from an equivalency. You just put one over the other and then you flip it over. Note there is no fixed density for salt water. It depends how much salt and how much water is used. In other words, molar mass, it's a fixed number. For water, it's 18.02 grams. 1 mole of water equals 18.02 grams of water. That never changes. It's how much does a mole of water weigh. But density can be whatever you want it to be. It's determined by the chemist. You can add as much salt or as little salt as you want to change the density. Mass percent gives the mass of a solute as a percentage of the mass of the solution. It's given by the formula mass percent equals grams of solute over grams of solution times 100%. You will encounter problems that give a solution in mass percent. Here's an example. A solution is 3.50 mass percent sodium chloride, NaCl. The question is, how do you deal with that in a problem? Since the problem does not say what mass is used, you get to choose the mass. And the mass you're always going to choose is 100 grams of solution because it's a nice round number and because it converts the mass percent to the number of grams. So we'll see that right here. Since the problem does not say what mass is used, you get to choose, and you will choose 100 grams of solution. 100 grams of a 3.5 mass percent sodium chloride solution will contain 3.5 grams of sodium chloride. Let's prove it using the mass percent formula. So 3.5 grams of sodium chloride over 100 grams of solution times 100% equals what we were given, 3.5 mass percent. So in other words, it converts the percentage to the exact same number of grams, and that makes the problem easier to solve. So you always choose 100 grams of solution, and therefore the number of grams of solute will be the same number as whatever that percent is, in this case 3.5. Remember, when you are given a mass percent problem, rather than a number of grams or moles, choose 100 grams of solution, and the grams of solute will equal the mass percent. The number will. Okay, now we're going to work the problems. What is the molarity? That's capital M of 2.3 moles of potassium hydroxide in 250 milliliters of solution. So identify what the problem is looking for and what it gives. This is something we've been doing in stoichiometry for the last couple weeks. So first thing you do, though, you always do this, almost always, there's one exception I'll show you, is molarity. It's capital M, but you convert it into its constituent units. That in this case, that's moles of potassium hydroxide over liters of solution. That's the definition of molarity. So you convert it to that. So on the right side is moles. We're looking for, it's asking what is the molarity. So we're looking for moles of potassium hydroxide over liters of solution. Over on the left side, you have 2.3 moles of potassium hydroxide in 250 milliliters of solution. Now, how did you know that you were supposed to put the 2.3 over the 250? Well, look at your final answer. It's got moles on top and liters on the bottom. So it makes sense to set them up like that. All right, now, with the way you deal with these types of problems, they're going to be two-story problems. They're going to have a top and a bottom, a numerator and a denominator. So the way that I recommend that you do them is you start with the top and you treat that like a separate problem. So the top part of the problem moves from moles of KOH on the left over to moles of KOH on the right. Therefore, no conversion is needed. You already have the units that you need in your final answer. The bottom must convert milliliters of solution to liters of solution. Why? Because molarity is expressed, the denominator is in liters of solution. So what's the equivalency we use for that? We need to get from milliliters to liters. So we use the standard equivalency, 1,000 milliliters equals 1 liter. That's true of anything, but we're interested in the solution. So we can create the two conversion factors. There they are. So which one are you going to use? Think about it for a sec. Pause if you need to. The answer is you're going to use the first one, 1,000 milliliters of solution over 1 liter of solution. Why? Because milliliters will cancel with milliliters. And so there's milliliters of solution on the bottom, milliliters of solution on the top, and we end up with liters of solution. Well, first we end up with moles of KOH on the top and liters of solution on the bottom, and that's what we need. So all of our units line up properly, so now it's time to do the math. So 2.3 times 1,000 divided by 250 divided by 1, and that gives you 9.2 moles KOH over liters of solution, or really the way to write it is 9.2 capital M for molarity. And the way it's read is 9.2 molar. Okay, next problem. How many moles of hydrochloric acid are there in 350 milliliters of 1.7 molar aqueous solution? So what's the question asking for? It's asking for moles of HCl. So identify what the problem is looking for and what it gives. Convert molarity into moles of HCl over liters of solution. The top part of the problem moves from moles of HCl to moles of HCl, so no conversion is needed. You see that right there. Now interesting, the bottom part begins with liters of solution on the left and ends with no units on the right. You don't see a denominator in the final answer. That means that the liters of solution must cancel. So we have the 350 milliliters of solution up there in the problem to help us do that. So there it goes from liters of solution to nothing on the bottom. So the bottom must convert liters of solution to milliliters because that's what the 357 is in, and then cancel with the 357 milliliters of solution. So again, this is all just a big puzzle. You're just trying to get units to line up so they cancel properly. It's the only way to do chemistry problems. So here we go. So we use the equivalency 1,000 milliliters equals 1 liter. So there it goes up there in the problem. And we need liters on the top and milliliters on the bottom because we need liters to cancel out. Then we need the milliliters to cancel out on the bottom because we don't have any units in the denominator or bottom of our final answer. So let's see if the units cancel. So liters of solution cancels with liters of solution. Milliliters of solution cancels with milliliters of solution. The last man standing, the only thing left is moles of HCl. So our units line up. So we multiply 1.7 times 1 times 357 divided by 1,000, and that gives us 0.61 moles of HCl. Okay, you want to create 500 milliliters of 1.2 molar sodium hydroxide solution. How many grams of sodium hydroxide would be required? This is a kind of a typical AP question. You're the student, your teacher says, I need you to create 500 milliliters of 1.2 molar NaOH. Why? Why do you need to do that? Well, you just decide that for some experiment you want 1.2 molar NaOH, and you don't want to make more of it than you need. You don't want to make you don't want to make 5 liters of it when you only need 500 milliliters, so you need to know the volume. So you know the volume and the concentration, so you have to know how many grams of sodium hydroxide would be required. So the numerator, the top of the problem, moves from moles of NaOH to grams of NaOH over on the right side. So you know what that takes. That takes a molar mass conversion. Moles to grams, grams to moles is molar mass. The denominator, the bottom of the problem, moves from liters of solution to no units, just like the last problem. So liters of solution must cancel out. So first, let's do the molar mass. We'll do the top first. Again, you treat these problems like they're two different problems. You solve the top first, and then you solve the bottom. So here we go. So the molar mass of sodium hydroxide, I did that for you here. It's 1 mole equals 40 grams of NaOH. It's exactly 40. So which one goes on top? Which one goes on bottom? Well, you're trying to cancel out moles of NaOH on the top over on the left, moles of NaOH. So you put it in that particular order. Moles of NaOH cancels with moles of NaOH. And the last man standing, at least for the top, is grams of NaOH. Now you need to get rid of the liters of solution. We're going to do that in the same way we did in the last problem. So the liters to milliliters conversion is 1 liter equals 1,000 milliliters, which then cancels with the 500 milliliters of solution. Okay, so we're going to go ahead and put that standard conversion of liters to milliliters, and then we're going to multiply on the top by 500 milliliters. Again, why did you do this way? Because it makes the units cancel. Watch. Liters of solution on the bottom left cancels with liters of solution. Milliliters of solution cancels with milliliters of solution. So the only thing remaining is the grams of NaOH. So now you're ready to do the math. Notice that there are no units on the bottom. All the units on the bottom in the denominator have canceled out and gone away. So 1.2 times 40 times 1 times 500 divided by 1 divided by 1,000 gives you 24. So you'd need 24 grams of sodium hydroxide. Okay, let's keep moving on. What is the molality of 3.7 moles of lithium hydroxide in 0.89 kilograms of water? So there's the formula. Molality is moles of solute over kilograms of solvent. And fortunately, that's what you were given. You were given kilograms of water. Water is the solvent. It's not the solution. It's the solvent. It's what the lithium hydroxide is being dissolved in. So this is a pretty easy problem. For this problem, molality is moles of LiOH over kilograms of water. So that's 3.7 moles of LiOH over 0.89 kilograms of water as given in the problem. You do the math on that, you get 4.2. And the way you should really express that in the final answer is 4.2 small m, lowercase m. What is the mass percent of 8 grams of strontium oxide in 45.2 grams of water? Okay, so for mass percent, everything has to be in grams, and you can see that it is here. So mass percent equals grams of solute, that's SRO, over grams of solution. Now that's not water. The solution is not the water. It's the SRO plus the water. It's the two of them together. That's the solution. And then you multiply that by 100%. So the solution is the solute plus the solvent. In this problem, the solution, the grams of solution, is grams of SRO plus grams of H2O. So we set up the problem. The solute goes on top, 8 grams of SRO. The solution on the bottom, it's the 8 plus the 45.2. Then you multiply that by 100%. And you get 0.15 times 100%, which equals 15%. So 15% of the solution is SRO. If 100 grams of solution is 5.2% NaCl by mass, how many grams of NaCl does the solution contain? All right, so this is one of these problems where I told you that if you're given a mass percent in a problem, you just assume that you're going to use 100 grams of the solution and then figure out how much of the solute, in this case NaCl, that you have. So there's the formula for mass percent. We've seen it before. So we want to find grams of solute. That's what's in the numerator of that fraction there. So you just set it up. 5.2% mass percent equals X grams of solute, some unknown grams of solute. That's what you're trying to figure out. That's your variable X. Over 100 grams of solution. We said you're always going to choose 100 grams. Then you multiply that by 100%. So divide both sides by 100% and multiply both sides by 100 grams. That's algebra, not chemistry, to get what X grams of solute is. So there it is, and that gives you 5.2 grams of solute. So notice that the grams of solute, when you choose 100 grams of solution, the grams of solute is the same as the mass percent, 5.2. So that just makes your problem easier to solve. You could have chosen any mass of the solution. You could have chosen 52 or 347, but why would you do that? Choose 100 grams of solution, and then your mass percent will turn into the same number of grams of solute. What is the mole fraction? That's the Greek letter chi. It looks like a big X, but it's chi, C-H-I. What is the mole fraction of 25.2 grams of potassium chloride in 102.4 grams of water? So the formula is moles of solute over moles of solution. You do not multiply by 100%. So KCl and H2O are given in grams and must be converted to moles. So what does that mean you use? That's right, a molar mass conversion. So the solution is going to be the two of them added together, but we have to get them into moles first. So there it is for KCl. The molar mass of KCl is 74.55 grams per mole. You put that on the bottom, so the grams of KCl cancel out and you end up with moles of KCl 0.34. For water, we know the molar mass of water. We've used that a lot. It's 1 mole of H2O equals 18.02 grams of H2O. Grams of H2O cancel and you end up with moles of H2O. In this case, it's 5.7 moles of H2O. So now you put the moles of solute on the top, that's the 0.34. The moles of solution, that's the two of them added together, is on the bottom. And you end up with 0.06. Even though it's called mole fraction, it's still presented as a decimal number, and it has no units of measure. It's just moles over moles cancel out, and you get just a number without a dimension to it, without a unit. So it's 0.06 in this case. What is the parts per million of 0.02 grams of arsenic in 2 kilograms of water? So we said this one is done, parts per million problems are just like mass percent problems, except the ratio is multiplied by 1 million instead of 100%. Parts per million measures are used when the amount of solute is very small, such as contaminants in drinking water, as we mentioned earlier. So there's the formula. So the grams of solute, first kilograms must be converted to grams by using the equivalency. This is a standard equivalency of 1 kilogram equals 1,000 grams. So 2 kilograms of water times 1,000 grams over 1 kilogram. Kilograms cancel out and you get 2,000 grams. So now you can go ahead and plug the numbers in the formula. There's the cancellation. So 0.02 grams of arsenic over 0.02 grams of arsenic plus 2,000 grams of water times 1 million, and that will give you 10 parts per million. So a very small amount. That still might be too much for drinking water for arsenic. I'm not sure. All right, we'll move on. Last problem. What is the molarity of 8 liters of 3 molar solution if it is diluted with 4 liters of water? So this is your lemonade. You made the lemonade too strong problem. You made the lemonade too strong, so you're going to pour some water into it to thin it out. So it's not as sweet, it's not as syrupy. Now there's a trick in this problem. You got to be careful in these types of problems. This problem is a dilution problem. If you make a pitcher of lemonade and you add too much lemonade powder, you would dilute the solution to make it less sweet. So it's a simple formula. It's the molarity before you added the water times the volume before you added the water is going to equal the molarity after you added the water. That's the M2 times the volume after you added the water. So the problem says that you are adding 4 liters to 8 liters already in the beaker or the pitcher if it's lemonade for a total of 12 liters. That's the trick. The V2 is not 8 liters or 4 liters. It's the two of them added together, and that's what you have to watch out for. So we have 3 molar on the left and 8 liters on the left. We're trying to figure out the molarity after you've added the water. So the volume at the end after you've added the water is, again, not 8 or 4. It's the two of them added together to give you 12. And when you do the math on that, that's just algebra, you get the molarity after you've added the water is 2 molar. All right, that takes care of your introduction to concentration problems. Again, that's when you mix 2 things together. One is dissolved in the other. The solute is dissolved in the solvent. And for this class, the solvent is virtually 100% of the time going to be water. And so these problems just take a little practice, just like grams to moles stoichiometry did. But if you do it, you'll get good at it.